Okay, so we've looked at the displacement of a simple harmonic oscillator in detail, and we've now found an equation for the velocity. What about the acceleration? Well, let's start with our oscillator doing the same as always. So we're going to start with it kind of at its maximum positive displacement and try and figure out through its cycle what the acceleration is going to be doing. Well, hopefully you remember Newton's second law, because it's quite useful in this instance. If I just draw on my diagram here that as usual, our displacement position x equals 0, and this is of course our maximum displacement x equals plus a. Well, F equals ma. That's Newton's second law. We all know that one. Well, what that means is that the acceleration of any body is always proportional to the resultant force acting on it. Well, when we've stretched our spring to the right like that, and we're just about to release it, we can see that there's going to be a pretty big force acting to the left, actually, isn't there? There's going to be the maximum force that it's ever going to have during its cycle, pointing to the left like that. So we can actually say that our acceleration there is going to be its kind of negative maximum value. Good. Okay, well that's a start, because if we go back to our auxiliary circle or helpful circle, then, well, remember that our body would be in this position and it's going to be moving around the circle at velocity v. Well, something that's going in a circle has at all times an acceleration with a magnitude equal to the centripetal acceleration. That's what acts on a body that's going in a circle, and we know that one expression for that is omega squared r. But of course the auxiliary circle is special because its radius is the amplitude of our oscillator. So we can actually write down that our acceleration, or at least the magnitude of our acceleration at all times, is going to be omega squared a. Now that's really interesting. In this position, the centripetal force is to the centre of the circle. So you can see that it's in exactly the same direction as it is for our oscillator. Just like with velocity, we were interested in the component in the direction of the line of the oscillation. So we actually straight away already have a value for a magnitude of our acceleration, and of course we just need to acknowledge the fact that this acceleration is going to be pointing to the left, so it's going to, and it's a negative maximum therefore. So we actually have our value that at that moment a is actually going to be minus omega squared a. So we're doing pretty good already. Well, let's get back our displacement graph that we are very familiar with now, our cosine. Remember, the equation of this graph is x, can you remember? X equals a cosine omega t. That tells us the displacement of our oscillator at any time t. If at t equals 0, it was at plus a. Well, thinking about the acceleration then, well, at that initial position, we already know that it's at its maximum negative. So that would be if we were to draw the graph on the same axis, but having a different scale for acceleration, well, that would be right down here. So let's go through our cycle like we did with velocity and see what happens as it moves through the cycle. So let's redraw our oscillator here and put him in the middle, kind of zooming to the left. So I'll put on the springs. So now let's think about this. What will be the resultant force if both strings are kind of stretched equally at that moment? Well, hopefully it's pretty clear as it zooms, the body on the auxiliary circle zooms across the top, and our body in our oscillator is going through the equilibrium to the left. Well, the resultant force is actually 0 at that moment, isn't it? Because the forces are balanced. And that means that, therefore, according to Newton's second law, the acceleration must also be 0. So we've got our point for the graph. It's going to be a quarter of a way through the cycle. It's going to be just right there. Let's just think about what that's got to do with the centripetal acceleration. Well, of course, centripetal acceleration is towards the centre of the circle. So at that moment, it would be pointing down, which has no component, has zero component in the direction of our oscillation. So that makes sense. That's why it makes sense that it's zero. Let's go for the next position. Let's put our oscillator now at the maximum negative displacement, just right there. And let's put on our springs and think about the forces again. Well, this time the force, because we've stretched it right out to the left, we can see that the force is going to be pointing the other way. It's going to be desperately trying to pull it right back to the right hand side. So we're going to have here our maximum positive force, maximum force to the right, and therefore our acceleration, according to F equals ma, is going to be our positive maximum value this time. And of course we know where that's going to be, don't we? Because the centripetal force of the body in the circle is always omega squared a. This time, as it shoots down this way, the centripetal force to the centre of the circle, so we can sort of draw it on going that way, and it's lined up perfectly with our oscillator. So it's pure horizontal, it's purely in the direction of our oscillator. We know that its magnitude is omega squared a, so we know our value for our acceleration of our oscillator at that moment is plus omega squared a. So we've got another point, and we can stick that on our graph at halfway through the cycle, isn't it there? Then it's going to be at our positive maximum. And we can start to sort of imagine what's kind of going on. Let's just do the point as it goes through the equilibrium again. So let's bring our oscillator to the central point. Well, of course, if it's in the middle, we already know what's going on. It's got no force, no resultant force. That means that there's no acceleration on the body. So A equals 0 for the same reason that it was 0 over there. And why does that make sense? It makes sense, just like before, because the centripetal acceleration on the auxiliary circle is pointing straight upwards and has no component in the direction of our oscillation, in the line of our oscillation. Great, so we've got the last point is 0, and we can put it there, or not quite the last, because then it goes back to the beginning, if we call that our last point, where it's going to be as it was at the beginning. And let's draw on our curve, which looks kind of something like this, which is kind of like a flipped over version of the displacement. Remember that, because later that's a really important idea. And let's do a pure graph. Let's give it its own graph, the acceleration. There we go. If the displacement was a cosine, we can see that the acceleration is a minus cosine. What's more, we've already nabbed the maximum and minimum values, amazingly. So we know that it's plus omega squared a for the maximum, positive, minus omega squared a for the maximum, negative. So we've actually got the equation. If you want to pause and see if you could write it down, give it a go. So the equation is A equals, it's a minus cosine, so it's minus cosine omega t, but the amplitude of our cosine is omega squared a. So it's A equals minus omega squared a cosine omega t. So it's kind of a bit similar to the displacement, but not quite. And we'll see exactly how they're connected soon. Well, last thing, so it's not left out, but let's put our velocity back. And remember, if you remember back to the last section, our maximum and minimum values of velocity were plus omega a and minus omega a. And remember, our equation was v equals minus omega a sine omega t. And so we've generated for an oscillator which is at plus maximum displacement at plus a at time t equals 0. We've generated an equation for the displacement, an equation for the velocity, and finally right now we've come up with an equation for the acceleration. Really valuable, and next we're going to see exactly how those are connected. So let's have a closer look at the connection between the displacement, the velocity and the acceleration of our oscillator. Now, can you remember the three equations of these three graphs? If you want to pause and see if you can write them down, feel free to do so. So the displacement was A cosine omega t, where A is the amplitude of the oscillation. The velocity was minus omega A sine omega t. And the acceleration graph is given by minus omega squared A cosine omega t. So now, if we look carefully here, we see something quite interesting. But first, remember that the velocity is the gradient of the displacement graph. Well, in the same way, the acceleration is also the gradient of the velocity graph. Well, that makes sense because we know in mechanics, don't we, that dx by dt gives us velocity and dv by dt, or delta v by delta t, gives us the acceleration. And if you're doing calculus in maths, then you'll be able to investigate a little bit that how those differentiate into each other. If you're not doing maths, don't worry about that at all, because we've derived these from first physics principles. Well, here's the really interesting thing. If we look at the acceleration, then we can see that it's minus omega squared multiplied by A cosine omega t. But A cosine omega t is the displacement. So what that means is we can actually write down an interesting link between the two. We can say that A equals minus omega squared, times x. Well, this is a really massive equation. It's a really important one. And it's sometimes described as the defining equation for simple harmonic motion. And so I'll write that down right there. And so it's a really important one to kind of recognise and to know how it works and what it means. So what it's really saying, of course, is that the acceleration of our oscillator is proportional to the displacement, but we knew that from our conditions in an earlier section. And the constant of proportionality is minus omega squared. Well, that kind of makes sense, doesn't it? Because we know that if we look at these two graphs, for example, the displacement and the acceleration graph, we can see that one's a plus cosine and one's a minus cosine. So they're kind of like opposites of each other. And when one's positive, one's negative. And if we think about our actual oscillator, when it's been pulled to the right, our mass spring system, the force is to the left, the acceleration is to the left. And when it's pushed to the left, the force is to the right. So that kind of explains that all over again. But let's see what that equation looks like graphically. If we were to plot the acceleration on the y-axis and the displacement on the x-axis, what would that graph look like? Well, if you want to pause, why not have a go, see if you could sketch that graph. It's quite surprising in a way that this graph is a straight line. Sometimes, if people aren't familiar with this graph, they kind of expect it to be some kind of wave, simply because we're talking about simple harmonic motion. But once you're familiar and you realise what it's saying, then we know why it should be a straight line like this. Obviously, when displacement is zero, acceleration is zero because they're proportional. And what we see is that when the displacement is plus a, the acceleration is minus omega squared a. And when the displacement is minus a, then the acceleration is plus omega squared a. And then it doesn't go beyond those 2 points because that's our maximum and minimum displacements. So what's kind of really going on is that the oscillator is shooting up and down this line. Well, in the acceleration world, it's zooming up and down that line. Okay, good. Well, one last thing. A really useful tool is just to bear in mind the maximum and minimum values for our three graphs, our three equations. We can write down here that our maximum value of displacement is, well, it's either going to be plus or minus a, simply because cosine can either be at a maximum, can be 1, and at minimum minus 1. But that's kind of obvious anyway. We know that our maximum displacement is plus or minus the amplitude by definition. The others aren't quite so obvious. But let's write them down. Vmax, our maximum possible values and minimum value of V are going to be plus or minus omega A, because when sine reaches its maximum plus 1, then we'll get minus omega A, and when it reaches its negative maximum minus 1, then we'll get plus omega A. So that gives us our maximum and minimum velocities of our oscillator, and we can do the same for acceleration, and I hope you can see that that'll be plus or minus omega squared A. So our max acceleration plus or minus omega squared A. Well, there's kind of a really nice progression there that, just to compare those, that we see, the maximum displacement plus or minus A, maximum velocity plus or minus omega A, maximum acceleration plus or minus omega squared A. And it's so useful to remember those. I really recommend it for exams, because questions often say, what is the maximum speed or maximum velocity of this oscillator? Or what's the maximum acceleration? And it can take a bit of thinking about, but if you remember these equations, you can write them down and pretty quick you can get to the answer. So a lot of maths going on in this section, but in the next few sections we'll look at some exam questions and some examples, and pretty soon you'll see how these work together to make life reasonably okay at solving simple harmonic motion questions.